Welcome everybody to our today's lecture on image analysis and processing, and image processing I should say. Although today we are doing a tiny bit of analysis. Now, it is the last lecture before the Christmas break, and I thought let's do something fun today. Alright, so you don't have to take notes. Let's see. It would be a shame if we had a problem. No, it's okay. Because today we'll have fun with Gaussian smoothing. So we spent a lot of time the last 3 weeks on studying filtering. After we studied the Fourier transform, we began to study filtering. And we saw low pass, band pass, high pass filters. And then we saw Gaussian filters. And then we took it a step back and saw mean filters and median filters. And then Gaussian filters again. And for all these things, we studied very efficient ways of how they can be computed. Right? And I said that of all the filters we studied, the Gaussian smoothing filter is probably the most important. This is because it has certain properties that make it very attractive. Right? And we'll talk about one of these properties later on today. But I thought, well, today let's have fun and let's have a look at what we can do now that we know how Gaussian smoothing can be computed efficiently. And there will be many, many things just like this one here. Yeah, you know, okay. One word of warning. Look at this slide. I said this is Gaussian glow. Whether or not that is true, I have no idea. So if you Google for that, you may probably find something else. So these terms and the terminology I'm using today, I made it up myself. Right? However, this is not totally random because if you use Photoshop or the GIMP, there are effects. I mean, there is all these menus with all the different effects you can use, and one of them is called glow. And from what I understood, it does something like that. See, there's something funny going on. I am talking about professional image processing software, and I don't even know what they are doing. But I can recreate what they are doing. Right? So I can sort of re-engineer what they are doing. And here is an example. So here is the input image F. And this is obviously a blurred version of F. Right? Let's call it G. And on the right hand side, I have created a new image H, which is a linear combination of these two. Right? So let us assume that this number alpha here is a value between 1 and 0, or 0 and 1. And so this is actually what we call a convex combination, because say if this is 0.8, then 1 minus 0.8 is 0.2, and together they are 1. Right? So if we add these two images with weights like this, such that the two weights will add to 1, we can rest assured that the result will not be much brighter or much darker than any of the original light. This linear combination, or this convex combination, will not take the result out of the range of the two images we had before. Right? And look at this, look what happened. I mean, isn't that pretty here? So my skin looks, you know, much cleaner. It's true, right? It's true. I like a little angel, and not just that, because this also this, you know, this sort of halo around me. Do you see it or don't you see it? If you don't, it doesn't matter. That's the beauty of image processing. Right? You can do things with images such that you know, your brain does not actively register that something is going on here. In that sense, all the examples we're looking at today are an indicator that you must never, ever anymore in your life trust any picture you see in any journal. It's true. Right? None of the pictures you see in today's media are real images. For all of these pictures, something like that has been done. And so if you want to, like, how is it that their skin is so beautiful? And how can it be that they are so, I don't know, skinny or have such a physical appearance? Like this is has all been doctored. Right? And sometimes these ways of doctoring with images are really, really trivial. So here's the input image. You see that, you know, it's like sort of my skin is noisy. And I blur it. And I add these two and we get that. And it looks most likely more pleasing. More pleasing. Here are a couple of examples where you can see, again, this is the original image, the input image. And then for the blurring here, we can use Gaussians of different sizes, right? Filter kernels of different sizes, which is basically to say of different variance parameters. So for instance, in the first row, it was 2.5, the variance parameter of the Gaussian kernel. In the second row, it was 5, so a larger kernel, and here it was 7. And I have chosen different values for alpha. So here alpha was 0.7, that is 1 minus alpha is 0.3, and here it was 0.8, 0.9, and there you go. And the image on the previous slide, I guess, was this one. So rather large blurring kernel, and not so large a value of alpha. Which is to say, so if we choose this alpha to be large, then the content of the new images basically comes from the original. Right. Let's go back to the equation. So if this alpha is large, then that says to create this image, take, say, 90% of the intensity values from this one and just 10% from this one. But here, I took 70% of the intensity from this one and 30% from the blur one. Right. There you have it. And images like that, you know, this is what you see in the journals, in all the magazines, in all the media. Never, seriously, I'm really very, very serious about this. Do not trust any picture you see in any media. They are all doctored. How did I do this? Look at this. That's all. So, basically, for all the examples that are to come, yeah, there's one missing, I guess. I did not import NumPy here. But what I do is I import the SciPy MISC module as MSC because it has functions to read in images. Right? This image was obviously a PNG image, so we ever so briefly talked about different image formats. Beauty of SciPy is you can use whatever image format on your hard drive. You just use this command to read them. And if they are being read, this will be a NumPy array of the corresponding size. And it will typically be an array of integer values. Right? So in order to turn it into an array of float values, I multiply this by 1.0. This is a trick I'm always using. I'm not saying read this in an S-type float. If you multiply it with a floating value, it will become a floating array. Yeah, and then, you know, remember last time when we had the exercises projects, I said, stupid SciPy, NumPy, they do everything for you now. And it's true, it's true. It's true, look, just one line. Just one line, right? So there is this SciPy module called NDImage, and it has numerous methods for low-level image processing. Among others, it actually has something that is called Gaussian filter. There you go, right? And here I'm just sort of setting two parameters. F is the input image, and sigma is like the variance parameter of the Gaussian. And here is how I create this new image. So if we have chosen sigma and alpha, well, it's just alpha times f plus 1 minus alpha times g, and there we are. And note that I'm using, I'm not using emsave to save the image, right? Not sort of the inverse command of this one. But what I do is I use the toImage function in SciPy-MISC, and then I am using .save to do this. The reason is that the sort of inverse command here, the imsave, automatically stretches the gray value range in your image to be between 0 and 255. Sometimes we do want that, for instance, if we want to visualize, say, the result of an edge detector. But usually we do not want that, right? Because this emsave does something to the image. It does another processing step. It's implicit. It's not obvious to us. I do not want the brightness of the image to be rescaled. And to avoid that, I'm using this command to save the image. Yeah, and the reason why I'm using this dot Gaussian filter is, well, I just discovered that it is there. It basically was you guys in the, yeah, it's true, right? Last time I checked, it's 2 years ago. I don't know if it was there back then, but now it is, and it really works. And so all of what we have discussed boils down to one line of code. The good thing is that you now know what this does, all right? You now, you have so much power over this line of code now, because you know what it does. So depending on what you choose here, and there are more parameters and we'll talk about them later, you really have a grasp now how to use these things. Okay, and whenever you are doing something like this, right, reasonable choice is to assume that this new image H is a convex combination of F and G, but be hackers. Always try to break it, to break the system. So what would happen if this alpha was not between 0 and 1, but say something larger such as 4? And this is what happens. Right. Here I have set it to 4. And this is the input image. This is the smooth version. This is the linear combination where I have chosen alpha to be 4 now. It's not a convex combination anymore, because if you add 4 and 1 minus 4, that does not add to 1. Right? And look at this, yeah, it gives you a totally different effect. Is that desirable? I don't know, but maybe sometimes it is, if you, I don't know, want to create something that looks old. Right? So this does not have a name on its own, but it just goes to show you that you can do a lot of stuff. And sometimes you stumble across stuff, you get results that are definitely not what you had in mind, but are interesting nevertheless, and so you may use them at some occasion later on. Okay, Gaussian glow. Now, what about if we do the same thing, sort of just for the edges, right? How I computed this shouldn't be a mystery to you anymore. You actually did it yourself. Here is an input image, and then we used a derivative of the Gaussian to compute gradients, and this is actually the resulting gradient magnitude image. Right? And it has found the edges, and as it was a Gaussian derivative filter I have used here, these edges are blurred. All right? So you know how I did that. And then, again, I create a new image. This time, I'm just adding alpha times G to the original image. And I've chosen that alpha to be 6. And can you see a difference between this image and that one?
There's slightly glow behind the hair.
And about here, right, like my jaw. So this is sort of the edges in the image are glowing now, right? Again, this is, and it of course has become brighter at certain parts. Again, maybe, I really don't know, but maybe this is aesthetically more pleasing. Something you might also find in the journals and magazines. Right? Here is what I did. No big deal. Everything that has changed is this line. The rest is actually the same. But I thought I can make it more interesting. Right? I don't know, let's say I was sort of a superhero and radioactively glowing. You see what's happening is this green glow, right? And sort of around my features. It's not where there are strong edges, but it's about the strong edges in this image. All of a sudden this is glowing green. How did I do that? How did I do that? Well, again, I'm reading the image, turn it into a float array. And then I'm just applying the gradient. Let's look at this Gaussian gradient maps. This is, damn it. You know, I didn't know that they are there. I really didn't, right? I didn't. But you know what they are doing, and so you can use them comfortably now, right? It's better to know what they are doing than to use them instead of using them and wondering what did I do here. Okay, I used this Gaussian gradient. It really does what it says it does. And then remember the very beginning of our lecture I said, well, there's a color image and intensity images, and we, for the sake of simplicity, always talk about intensity image. But a color image is just 3 intensity images. We have a red layer, a green layer, and a blue layer. We'll study colors later on in January. And so what I did here is I set the red layer to the intensity values I've read from this. This was actually an intensity image. So that all the red values should have exactly sort of these intensities, and all the blue values should have this intensity. And then just for the green layer, I applied this addition with this Gaussian edge magnitude image. And then I created a new image, which now consists of 3 layers. So this is a 3 by 256 by 256 array. So the XY resolution is 256, and then we have 3 layers. This is what this does. And I am writing this to disk. And the result is this one. Okay. What if you wanted to pretend you were a time traveler? Right? And there was some picture of yours taken in 1895. So you take your original image, you smooth it using a Gaussian, and then you add some noise. Right? First you smooth the image, and then sort of you add noise to the smoothed image. And then you colorify that image like this. And all of a sudden it looks as if this portrait would have been taken like 100 years ago. Can be done, no problem. How did I do that? Well, okay, I assume we all know now how to read such images from this. I determine the y and x dimensions of the image, so the number of rows, number of columns. I call them y and x. Note the flip here, right? It's not like with the x derivative last time. So this is the number of rows in the image, this is the number of columns. Well then, given the input image, we just apply the Gaussian filter. And I am choosing a certain sigma smooth, I call it, as the size of the Gaussian filter. And now given this image G, the smoothed version, I am using the numpy function random.randn for random normal. So this gives us a random number drawn from a Gaussian distribution. And actually, if I call this function with the size of the image as the 2 parameters, it just does not just give us one Gaussian random number, but actually an array of the size xy, and all the numbers in here will be random numbers drawn from a Gaussian distribution of variance 1 And therefore, to sort of, and those typically will be values minus something close to 0 plus something close to 0. So in order to increase these random numbers, I multiply them with another sigma value. So I have sigma for smoothing and sigma for noise. This gives us this. This is the second line of code here. And then I want to create this colored version of the image, where the color is basically a very dirty orange or a very bright brown, depending on how you want to talk about it. Right? Let's say a very bright brown. And expressed in red, green, and blue values, this brown could be 162 in terms of red, 138 in terms of green, and 101 in terms of blue. What I do here is I first compute the average of all the intensity values in this image. And I want to create a color image whose average color value is in the 3 channels given by these 3 numbers. So what I'm doing here is I sort of look at the difference between the target color value and the average value in our noisy image. It's sort of if, say, M would be larger than 162, this would be a negative number, and we would have to subtract something from our intensity image for every pixel. If it was something less than 162, this would be a positive number, and we would have to add something in our intensity image to get this corresponding average of 162. So by this, we have this noisy image here. It has an average intensity, mean, and I want to turn this average intensity for the red channel into 162. So either I have to add or to subtract something to our current mean in our noisy image H. And for the 3 different color channels, I have different target average intensities. And this is just basically to say this gives us a way of setting the average intensity in the red, green, and blue channel given the noisy image we have here to these 3 values. Okay, this is gives us this. Because we do have intensities in here. Some of them are bright, some of them are dark. On average, they have a value, let's call it M for mean. And we want to have a red channel that has an average value of 163, what was it? 62. We want to have a red channel where the average is 162. Now, if the average of this image is something less than 162, we should probably add something to reach this target value of 162. If it's something more than 162, we have to subtract something. Right? So we have an average intensity here, and we do want to have 3 color channels with target average intensities. And if we do it like I showed in the code, we get this. Again, I do not know if Photoshop or GIMP do it this way. But this is not the take-home message here. The take-home message is that if you want to do something with an image, you can sit down and think how to achieve that effect and then do it and typically get it. Yeah, so that was that. Or now this one. Do you remember, again, at the beginning of the lecture, when we first talked about coordinate transformations and we looked at it from a point of view of geometry, and I said, we can think of an image as a function defined over x and y coordinates, but just as well, we could think of the image as a function defined over r and phi coordinates. Then we had a brief discussion if this is a true representation of this idea or not, but Here, what we see is that this axis represents the radius taken from the center of the image, and we see these 4 peaks here along the radius axis. This is actually are the 4 corners of the image. And this axis represents an angle, and that one goes from 0 to 2 pi. And so I have turned this image into that, and that's all good and well. We ever so briefly talked about this, and we'll come back to that in January. And then what I did is I applied a Gaussian filter, a one-dimensional Gaussian filter, to the colors of this image. Okay. What will happen if I transform this back into the XY representation? We have taken the image in the XY representation, turned it into an image in R phi coordinates, and now I blurred along the phi, the angle dimension. Okay, to make a long story short, here it is. You can achieve this differently, but pros do it like this. There's other ways of how to. This is by far the fastest. Right? You could actually try to come up with a filter mask that is sort of looks, arcs instead of rectangular areas. That's a nightmare to program. Can be done. Idiots do it like that, but it's actually rather easy to go from here to here. Once we are given this image, then to do a blurring along the phi direction is a triviality, and then we have to transform this back into this representation, and this is what we get. And funnily enough, my eye is very close to the center of the image, so it looks like, it has been blurred radial, angular. Right? The blurring is sort of now it's circular. Okay. Focus on this one while I switch the slide. Ready? Go. What has happened? I have now blurred it along the R direction. How will the resulting back transform look like? It will be blurred like this. We now have, so it looks as if the camera has zoomed in or out really rapidly. Right? You can create these kind of effects. There's no problem here. This is radial Gaussian blur. Can also be done many different ways, but this is how smart people would do it. And here's the code. No, wait, here's another example. I love this one. This is more, it's sort of, very pronounced because it's strong edge image and so on and so forth. Also, note artifacts around the boundary of the image. There's nothing we can do about that. Right? It just so happens. Those are things that are being interdicted. It shouldn't be there because everything is white here, right? But that again depends on how we compute these transforms. So there is lots of black pixels. We'll discuss that in January. Because if we go from here to here, there will be combinations of R and phi for which there is no value in here. Right? So for instance, there might be a very large radius somewhere in an angle. I don't know, so say this here corresponds to this line segment, and if I were to rotate this, so we have for this very large radius, there are lots of image pixels that are not really in the image, and I'm setting them to black here, because what else can I do? I don't know their value. And if we do this with this image, this is the reason why it is so dark here. Again, because there are lots of values in this representation where we don't know what to write there, so I set them to black. This causes nothing we can do. And of course, if you really want to, You could, for instance, for the Asterix image, set them all to white, then it wouldn't be there, but this was too much of a detail for me to bother about. So here you go, is the angular blur, here is the radial blur. And also the fact that the center pixel is a bit pronounced is probably something you don't really want to have in practice. You can, some if statements or some additional blur can be addressed. I didn't care about it. Why should I have it? Don't have to, right? Can be done, no problem there. So if you're not happy with unpleasant artifacts like that, you can, a couple of if clauses in your code and they are gone. I didn't bother. No code for this one. As I would interfere with the current project. You have to figure out that for yourself. But I can tell you, like, I did this in Python. And actually I did it over the weekend. So the examples, some of them we may have seen on during the lecture already, like this one. So all of them I have shown you up until today. I did in C, and I did them years and years and years ago. There was no SciPy ND image and stuff like that back then. Right. So most of the images we have seen throughout this lecture so far have been processed using C code written by myself years and years ago. And this weekend I sat down and everything you see here has been done in Python. Right? So I can now for myself know that you can do those projects. Of course I knew that you could do that even before I did it myself, but now I really know it can be done. I did all of this in Python, and I'm not showing you the code because you'll have to work on something extremely similar. And I would give it all away if I were to show you the code. So no code here. Yeah, and then how to say something more serious, I don't know, something more in the area of image analysis. And I'm showing you this just to sort of corroborate a claim I made earlier. Remember that we talked about the idea of difference of Gaussians. We have an image, we smooth it with one Gaussian filter, and we smooth it again with another Gaussian filter, and we subtract the two smoothed versions from each other. And here are a couple of such differences of Gaussians. For this one, this one here was the input image. Here, the two Gaussian filters were chosen such that the variance was rather small. I don't know, say 1.2 and 1.4, for instance. And here, the variance was rather large. That is, the two images I subtracted from each other here were severely blurred versions of this one. But all the images here, all those 14 images, are actually differences of Gaussians. So they result from subtracting two smoothed versions of the original image from each other. And then once we are given such a number of difference of Gaussian images, these are 14, we can create a three-dimensional array where we stack this one on top of this, and so on and so forth. So we create a stack of images. We are now given something sort of three-dimensional, and it has an x and a y dimension corresponding to the size of the image, and it has an x dimension corresponding to the number of difference images here. And in this cube or stack of images, I am now iterating through this, like layer by layer by layer by layer, to find local maxima and minima. Imagine these things are all stacked on top of each other, and then we iterate through this, like to this whole stack of pixels. And we are looking for a pixel that is the largest with respect to its, let's take A pixel that is the largest in its local neighborhood in this plane. So say this very bright pixel is maybe larger than all its 8 neighbors. Right? All the 8 pixels surrounding this one. But there is an image on top of this and an image below. And this pixel does not only have the 8 neighbors in its own layer, but there are 9 pixels immediately on top of it and 9 below. And if the pixel is the largest among these 27, I guess, no wait, 28, no 26. If a pixel is the largest pixel with respect to all its 26 neighbors, the 9 on top, the 9 below, and the 8 surrounding it, then we call it a local maximum. If it is smaller than all of the 26 neighbors, we call it a local minimum. Given this stack of images, I am now looking for local maxima and minima. And here they are. Here they are. Those are the coordinates, the x, y coordinates of all the, well, I filtered somehow, most of the local maxima and minima we found. And the size of these boxes indicates sort of in which layer they were found. The larger the box, the deeper in the stack this local maximum was found. The maximum was found. For instance, if say this pixel here is larger than the corresponding pixel here or here, and larger than all the pixels in its local layer, it would be a local maximum or minimum, and it would have a rather large square here. It's just to indicate sort of the size of that. And let us try to understand what's going on. I said when we discussed difference of Gaussians that we can understand those difference of Gaussians as a mechanism to detect image content that is salient, and salient is a fancy word for it sticks out. So, for instance, let's look at this severely, sort of the result of the subtraction of 2 severely blurred Gaussians. We have a dark blob here and some dark blob here. What are these 2 things? It is this one and this one, right? And the funny thing is that these 2 blobs appear, do appear here just by subtracting blurred versions of the image from each other. This subtraction mechanism does not know that this is an image. It does not know that it shows 2 comic characters. And it does not know that one character is here and one character is there. We know that because our brains can do that. Right? But the algorithm I used here, is just additions and subtractions. That's all there is to it. And nevertheless, there are these blobs. And it so happens that these, thick blob-like features here correspond to semantic components of the image, to the 2 characters we see here. In that sense, these 2 things here are salient, something that sticks out, something our eyes like to sort of focus on, or would recognize as a coherent, a compact subpart of the whole image. This works beautifully in this case because there is a lot of white. It would not look as nice as, as it does here if this was a more complex scene. So I'm tricking you. Careful, you have to be careful. Right? This is chosen on purpose, this example. But we can see that there are substructures in the image. Now, if we do this with smoothing masks that are not so large, we see again like certain dark blobs here. And these are, for the breaks of the oblique characters, they become apparent here. Right? And if these blobs sort of survive over different layers in this stack, that is, if some of the pixels belonging to these blobs are local maxima or local minima, we select them, and here they are. And so what we can see is, indeed, there are these red squares I'm using to indicate the location of local maxima. For the braids here, there is one for the belt of obliques, for this thing. Actually, the others have that too. Note that they are slightly moved to the side. Right? Yeah, this is something that it is like that. It's an artifact due to the mechanism we apply in order to find these blobs. There's not much we can do about it at this point. We will later. Right now we can. But again, it would be so much nicer as if this red square was exactly in the center here. It is not. But if I would have applied an additional processing step, I could have moved it there. We're not discussing that. All the things we would say, okay, are sort of locally coherent, like this white blob here has a corresponding red square that indicates there's something salient around this thing. The little dog has been identified as something that is salient on certain scales. And so. The funny thing is that there are these things outside of everything, something we would not at all call salient, something we would not refer to as something important. But look at this. It is actually there. Right? It's like, because of the blurring and then the taking the difference between these birds, certain regions, because at a very high or very coarse resolution, there is something dark here, then something bright, and then something darker again. And if we apply these Gaussians and subtract them, which is a way of sort of another gradient, it finds this transition from something dark to something not so dark to something darker again. And this transition may actually be due to something that has nothing to do with image content. Again, this is something, this stupid algorithm, there is no intelligence here. This stupid algorithm cannot realize, this algorithm is not an artificial intelligence algorithm. Right? In order to get much better results than these, we would have to apply much stronger tools. And of course people do that because people are interested in understanding what's going on with the image. We will discuss that later. Okay, that was that. Here is how I did it. I said I convolved the image with different Gaussian filter kernels, and here they are. So I have 1.2, 1.4, 1.6, 1.8, 2.0, and then we have 2.4, 2.8, 3.2, 3.6, 4.0, 4.8, 5.6, and so on. Note that this row, or this row is 2 times this row, and this row is 2 times this row. These are called octaves. This is how people do it. And also note that I multiplied all these values by 5. So instead of convolving it with 1.2, I actually convolved with 6.2, right? And so on and so forth. But this is how I define these 3 octaves. And then depending on the size of the image, I have to choose something here. So again, that is my intelligence that put the times 5 here. It is not the algorithm. I did it. And then I initialize an empty list and I iterate over all these numbers. And for each number I create a blurred version of the image and insert it to this list. And then I initialize another empty list and now iterate over all the images in this list here, which now contains 15 images, but I actually only iterate over 14 of those, because here I compute the difference between image I and image I plus 1. And this difference is appended to this list here. So once I'm done, I have a list of 14 difference of Gaussians, dogs. And these I turn into a 3-dimensional NumPy array. Can be done, this is no problem. This is a list, and this np.array applied to lists creates an array. And then there are interesting operations, maximum and minimum filter, I can apply to this stack. And the 3 here says that I actually really just want to look at the local sort of 3x3 neighborhood of every pixel, finds me the local maxima and minima, then some Python stuff to actually get only those pixels where any pixel in this new array actually is contained in here and is contained in here. This is NumPy stupid stuff. And then I compute the indices of all these pixels using NumPy where it is either true here or true there. This is an OR operation. And oh, that was it. Yeah, this is what I wanted to show you here. I could have done this differently. Let's not discuss that. But the important thing is, with respect to what we have done so far, we again recognize the call of the operation or function Gaussian filter. And here's something interesting. This time I not only provide 2 parameters to this function, but 2 more. If you look into the docs manual pages for this Gaussian filter function in SciPy and the image, you see that we talked about what to do along the image borders, and it gives you lots of opportunities. It says either you can treat those image borders as a constant value, pad them with something. I actually padded them with white here, right? And that makes sense because the image is very white along, not with 0 that is black. You could choose reflect, wrap, lots of stuff here, and then it's horrible. It's horrible. There's nothing for you to do anymore. It does everything for you. It's true, right? It's true, and you don't even have to, it's basically 4 times hitting return. So you do all this. You choose constant, doesn't look good. You choose wrap, looks better. You choose mirror, looks best. Bam, done, right? So you don't even have to write tremendously different code. All you have to exchange is this 3rd parameter. It's horrible. But it's good. It's good because, in a sense, humankind becomes more productive, right? But again, you now understand why these additional parameters are there, because we discussed in detail what could be done along the image boundary, right? It could be set to something constant. It could be mirrored or reflected, or whatever. And actually, I didn't know it, but now I do. It is there, and it provides you with different options. Okay, here is something funny. This is, note that the last example we discussed was already something in the direction of image analysis. Right? Here is something more about image analysis. This is an image that was obviously taken by a professional photographer. And this is obvious because whoever took this picture used a manual focus. Right? So typically your camera would try to make everything sharp. But from the point of view of aesthetics and photography, it's quite often really interesting to focus on something in the foreground or focus on something in the background. Images like that have high aesthetic value. And here, obviously, and I can really say that, this barbed wire fence here was focused upon, and there is, I don't know, some scene with horses on some meadow with mountains in the back, so probably Rocky Mountains, who knows, I don't. But apparently this scene consists of something in the foreground and a lot of background. And the question is, can we automatically separate the foreground from the background? can we automatically determine what is in the foreground? We can. I did it in Python, I'll show you how. So, I wrote a little Python script, and once that was done, it produced this image. So apparently, it was possible to realize that this part of the image, and I am deliberately not calling it the barbed wire, but there is a certain part of the image that is sharper than the rest, and therefore is sort of the part of the scene that the camera was focused on. And I can extract that automatically. It's an image analysis task. However, this algorithm does know nothing about barbed wire. And all it knows about is sort of sharpness or local contrast. Here is how I did that. I first turned the color image into a grayscale image. Why did I do this? I could have computed all of what is to come with the color image, but it actually works if I first turn it into an intensity image. It's easier to work with. And then I compute the difference of Gaussians, just as we discussed. But this time I choose the two variance parameters to be really, really small, or comparatively small. For the one Gaussian it was 0.5, and for the other it was 1.0. And if I apply this difference of Gaussian filter to this image, this is what we get. Let us briefly think about why that could be the case. Now, we are given an image which is in large parts very blurry. And there is a certain part in the image that is sharp, or something we would call sharp or focused upon. If I apply two tiny, really like small support, Gaussian filters to something that is blurred, not much will happen. Because this is blurred already. Right? It's blurred already. But if I apply, even if it's a small Gaussian, to a part of the image that is sharp, it will become blurred. And so therefore, if I apply two Gaussians to this, one smaller than the other, in parts where the image is blurred already, the difference between the two additional blurring steps should be, neglectable, close to zero. And it is. Right? Here actually a note that to save this image I used IMSave. So this is not what's really there. This is an artifact or a scaled version of the image. So instead of being 0, this is some dark gray here. But this is because of the way I saved the image. But I did it because if I would not, it would be so, all the values would be so small in here, we couldn't see them. It would be basically a black image. So here I scaled the intensities. And so therefore what should be 0 is actually a darkish gray, because there are certain parts, of course, that difference of Gaussian is some sort of a gradient operator, and if there's some brighter and some darker parts, brighter and darker parts. And the darker parts here actually, minus something, and the gray here is sort of 0, and the bright parts are plus something. This difference of Gaussian. But once again, where the image is blurred already, if we apply two additional blurs and subtract them, the two additional blurs shouldn't do anything to a blurred part of the image, and so if we subtract them, it should be 0. And we find that here, and can you see the very, very weak outlines of the horses? So they are, it's very blurred here, but still, if we apply two more blurring filters, subtract them, we find the edges of the horses. But again, where the image is sharp, this blurring will make a difference, and so therefore the fence, the barbed wire, sticks out. But again, the algorithm does know nothing about barbed wire all it does is two blurring operations, subtract them from each other. Now, then I take the sort of absolute value of this image. Right, so like there's something negative here and something positive. Bright in this representation is some positive values, very dark is some negative values, and gray is basically 0, but this is just a visualization. So I take the norm, the absolute value of that, so something that is very dark also becomes something of a high value, something that is very bright becomes something of a high value. So I do this, and then on this absolute value image, I again apply this maximum filter. I determine like which pixels are larger than some value, some threshold. And this gives me that. And this, I note that there are some white and gray pixels in here. I turn them all to white. That gives me a binary image, and on this binary image I then apply something we have talked about earlier, like this erosion, dilation, opening, closing, blah blah blah. There are some holes in here. I don't want the holes, and so here you can actually see a practical application of what we discussed when we talked about morphological operations. And here is the code. So I read in the image, it is a color image. F is a color image. The red channel is the first layer in this color image. Green and blue are the second and third layer. And I turn this color image into an intensity image using this funny weighted combination here. The reason for that will become clear in January. But we're given a color image and I turn it into an intensity image. Then I do compute two Gaussian smooth versions of the image. One with a sigma of 0.5 and one with a sigma of 1.0. And note that this time, you know, I played around with it. Actually, Reflect gave better values here. And it's, you know, I just have to hit return, look at the result, hit return, this looks better, I'll take this. Okay, so that is what happened here. I subtract those two, and I call the result k. I compute the absolute values in k, and then I set everything in k that is less than 10% of the maximum value to 0, and everything else to 1. So I turn this into a binary image. And then there's nothing you have to do for yourself anymore, like seriously. Then actually this SciPy ND image also has all the morphological operations built into it, so yeah, I just use them. There you go. Right? I use this dilation, we talked about this. There is another one that fills holes, we didn't talk about that. That is, this is an algorithm from originally developed in computer graphics, but it is there, and as it was there, I happily used it. And wait a minute. Okay. This should be called O now. I know that I changed the program after I created the slides, so this is why it's called O here. This should be M. I'll change that before I upload it. So we create this binary image, right? Sort of which now contains 1 for a sharp pixel in the original image and a 0 for everything else. Binary image, we sort of expand this a bit using dilation and close the holes. This gives us an image M. I deleted a line here, and so this is why it's still called O here. But this should be M, not O. I'll change that. We have this binary image M, which contains a 1 if the input image is sharp at this pixel and a 0 elsewhere. And so therefore, we multiply the red channel with this mask. It will be lots of zeros. but some of the pixels will be multiplied by 1. They will survive that. If we multiply something by 0, it will be 0. Do this for the red, green, and blue channel and create the final array, and that gives us this. The color image, we magically have computed a mask that sort of identifies the foreground. We multiply this image with this mask, and that singles out the foreground. There you go. This is how we do that. That is image analysis on a very low level. Now, as you may be tempted to believe that you now know how this is done, I have to show you that things are not so, you know, this is the sad part about this lecture on image analysis and image processing and image analysis. The fun part is that, so what's really funny about image processing is, by now you know it involves a certain amount of mathematics. But the great thing is we can see the mathematics in action. Right? You hit return and you see something, yay! You know, you can see what this does. This is why it's fun. The bad thing about all of this is that things are not so easy. Right? That you might be tempted to believe, okay, now I know how to determine foreground objects. Look at this. Here we have another scene with a funny dog in the foreground, and the dog is much sharper than large parts of the other parts of the image. And I applied the exact same code. Right? The code that filtered out the barbed wire does this. This is not so bad, actually. It's not so bad, but it's not as good as in the case of this barbed wire image. If I was really interested, and I am not, but these are just examples I did over the weekend. If I was really interested in separating the dog from the background, the first thing I would do is to see what happens if I choose different values here. I would keep all the code as it is and play around with this, with the two sigmas for the Gaussian smoothed versions of the image. I said, play around with this. This is, how do you do that, right? Well, you can pour yourself some coffee and plan for 2 hours of what happens, you know, trial and error. And seriously, trial and error until it looks good. It may never happen that this. Next thing is I would play with this value. See if it makes a difference here in this suppression of non-maximum values. This I would leave intact, but there are 3 parts in our program where you might want to try to adapt them to this situation. And this is of course horrible, right? Because if you do it systematically, you have to keep 2 of these 3 parameters fixed and vary the 3rd. Then you have to keep 2 others fixed and vary the 3rd. Then you have to keep, and here, you know, with 3 parameters, it's okay. It's okay, right? It will take some time, and you will eventually get there. If this would depend on 50 parameters, you can forget it. It's just like that. You know, there's nothing you can do. And we already see that the difference between image processing and image analysis is basically that processing is about transformations. We do something with the image we are given, we create something new. And analysis is a lot about trying to optimize certain results. And mathematical optimization is something else than what we're discussing in this lecture. Right? But we'll get back. So yeah, unfortunately, it does not work so well. It is nevertheless a very good first result. And by varying these 3 parameters, we could probably turn it into something better. And ideally, there would be a way for us to vary these parameters automatically. And the science of sort of varying these parameters automatically to extract some meaning out of an image is called computer vision. There's a difference between image processing and computer vision. Computer vision is all about extracting meaning of an image, in the sense like finding the foreground object is a very simple example of extracting meaning of an image. Here's another example. Exact same code. Right? Something in the foreground that is focused on, and some background, and yeah, we have these artifacts, like funny stuff. There is stuff that shouldn't be there, in the sense that, okay, it is sharper. You know, it makes sense. There is a very sharp edge here, but we as human beings would not consider it to be the foreground object. And then also, this is not closed. There is this hole here. If this pixel here would have been recognized as a foreground pixel, this hole would have been closed by the hole filling line of code. But as it was not recognized as a foreground, so this appears to be not sort of sharp enough. Where is this? Here. This, you know, obviously too blurred for this simple algorithm. Again, we could play with the sigmas and with this threshold. For the configuration I used here, was not recognized as a foreground pixel, and therefore there was no hole to fill. Because this is actually a concavity here. If this would have been closed, the algorithm would have closed the hole, we would see the whole flower, but we have large black things here because of this hole in the boundary. We could do something about that. If I would want to, I could run further dilation steps to, you know, make sure that tiny holes are being closed. But you see, this again would involve my intelligence. The algorithm I've used here is really stupid. Given that it is so stupid, this is an interesting result. Very stupid processing can create rather interesting, or for us, reasonable results. But to make these results better usually requires human intelligence to be turned into program code. Yep. So that's all for today. We now know about practical applications of Gaussian smoothing. There you have it. This was a bit of fun for the last lecture before the break. Are there any questions? Great. Then I do want to wish you all a very nice and relaxing break and a happy new year, and we see each other again in January. Thank you.